Hello and welcome back. Moving on to day 6, 2025. So um, for this one, our problem input is we get a series of math problems. Each math problem is kind of delimited along these empty columns here. So if there's all spaces in a column, we can assume that that's um, like a boundary between one problem and the next. On the lowest row, we get a series of operators. There are two that we have to care about, addition and multiplication. And then the problem is basically, moving top to bottom. You apply the operator, kind of like a plus reduction or a times reduction. And then you get a series of results and you add all those results up and that's your answer. So here in part one, this means like this first problem would be 123 times 45 times 6, and that equals some number. And then like 328, 64, 98, you add all those up and that's another number. So perform all those operations and add up all of the results. For part two, it's kind of the same story, but there's a wrench in things here. So for part two, so if we consider each problem individually, for part one, we were reading each of the numbers left to right. And for part two, we read them top to bottom. So for this first one, rather than 123, 45, and 6, reading top to bottom along the columns would be 1, 24, and 356. Now you still use the same operations, it's just the numbers in the problem that are changing. And the tricky thing about this is that now the white space is significant, right? So this 6 over here is like right justified within the problem, which means that it gets read as 356 rather than some other number. And in the second problem, you can see that these last two numbers are left justified, which means that 8 is hanging out by itself and should be parsed as the number 8. So that makes things a little bit trickier. So the biggest kind of problem, like this is a fairly simple problem on the face of it. The tricky part is doing the parsing correctly. And it would be cool if we can come up with some sort of like generalized parsing thing, or like parse these numbers into some structure such that we could reuse it between part one and part two, right? So that's the problem. Let's go ahead and just use the real input today. So we'll do 202506 txt1. This is our input. We can mix it together. It's pretty big, by the way. So if you, I don't know, maybe some editors have problems with like super wide lines, but we're looking at 3,700 characters wide for each line in any case. Okay, so normally I would do something like this. I would do like, space, not equals, maybe like this for each one of these, and then we could like mix it together. And this is normally how I would parse something like this, right? So we get all of our numbers, we get all of our operators, everything's fine. The problem is that we lose the information. Denoted by the white space. So you can see here in the second problem in our input, the last number, 47, is right justified. And if we just parse it this way, by throwing away white space, now this is this is just 47 by itself, we won't be able to, like just with this structure, it would be hard, if not impossible, I guess, to determine the proper numbers for part 2. So instead of just splitting on white space, let's go back to this. Let's split on the empty columns. So we'll split along the boundaries for each problem. We can do that with space not equals, which turns this into a Boolean matrix, and we can do an OR reduction. So see how like, so in this column it's all zeros because none of those characters are not spaces. So basically if there's at least one character in the column that's not a space, then if we do an OR reduction along the columns here, then it'll show up as a 0 in the final Boolean vector. If you want to be fancy with this, by the way, you can do this as an inner product. So OR dot not equals same number of characters, but you get extra inner product points, I guess. And then we can use this as a partition Boolean vector. So if we assign like P here for our mixed input, we can use it to partition. And we get this. And now if we look at this, see how 47 was, so previously 47 was, just like a 2-character string basically. And now it has the extra 2 characters of white space, or 1 character, I guess. So this would allow us to recover, the white space is going to make it easier for us to determine the part 2 answers by reading top to bottom. So we will assign this to P. And let's go ahead and parse. We're not quite done with our numbers here, so let's do a little more parsing. We'll do -1 drop to get rid of that last row. We'll handle the operators in a second. And then let's transpose this. So the columns are now rows, and we can split it. So each row is considered independently, and then for each one of those rows, we can mix them together into a matrix. So this is even nicer. Now each one of the numbers in our math problems is parsed out into a rectangular block. And we can manipulate this pretty easily to figure out our part 1 and part 2 answers, right? Now these are still strings, so we'll need to turn them into numbers at the appropriate time, but we will get to that. Let's call this like M for matrices, I guess. Okay. What about our operators? Well, we can get our operators by taking the last row of our input, and because the input is set up in such a way, we can see that the operator appears in the first column, appears in the first column of each math problem. So here we can just do a each first. And now I'm going to do something a little interesting. Let's do like times plus outer products equals. So this is a technique that I'll use sometimes. I call it like a selection matrix or something like this. So when you have like a bunch of data that you need to conditionally do some operation on, one option is to use conditionals. Surprise, surprise. So you could construct like a defense or a function where you're testing some conditions and you're like, okay, if the operator is this, then do this, otherwise return this other thing. But it can oftentimes be shorter, more terse anyway, to expand all this into a matrix and then calculate all the possible values. And then if we multiply this selection matrix times um, you can imagine like for each math problem, if we like add them all together, or if we multiply them all together, so sum and product, this selection matrix would allow us to pick either one of those results. And so it's often terser in terms of the final length of your program. And even though you're calculating a lot of data that's not going to be used in the final problem, so you're doing like a lot of unnecessary calculations, depending on how you do it, it can be quite a bit faster. Because with conditionals, branching, CPU caches, I'm like waving my hands here. But it can be faster to just do like a vectorized operation, especially if you're working with flat matrices. And you're calculating twice as much data, but you're doing it much faster each time, so it ends up balancing out. But anyway, hopefully this makes sense. Let's call this S for selection matrix, and that's pretty much all we need to do for parsing out our operations. All right, so let's look again at our matrix. We're going to want to do something with this, so let's go ahead and start building a function. Probably a good thing to do would be, so first let's split. Yeah. Omega. Yeah, so first we can split it into rows, and then for each one of those, we can finally do execute to actually turn them into numbers, which it doesn't like because I need an extra each. And now, so the cool thing about this, so by splitting the input into rows and then executing, we can, like this works just as well for part 1 and part 2. The only difference is for part 2, we have to transpose each of the character matrices. So like if I do this, this is literally all that we have to do between part 1 and part 2. So let's take a look at our matrix here, and we can see so for part 1, it's 46, 73, 48, 69, 283, et cetera, which matches kind of what we'd expect for part 1, just reading top to bottom. If we read along the columns, we get 44, 24, 68, 84, 76, 31, and 39, which is what we get for the function that we're building if we just transpose the input. Now, normally I would, in a heartbeat, like mix this, right? So, we're parsing everything out. There should be the same number of elements, but in this case, there's not the same number of elements. For part 1, we're always going to have 4 numbers in each problem, but for part 2, the number of numbers is dependent on how many digits are in each number. So for this problem here, because there's only, each of these numbers are 2 digits wide, when we read along the columns, we only get 2 numbers out. And then when we mix it, it has to fit into a rectangular array, which means that the elements that are missing get padded out with zeros. Sometimes this isn't a problem, but it is a problem for us because we're going to be doing a times reduction along this row, and anything times 0 is going to be 0. So rather than handling these zeros, we'll just work with our data here in these boxed rows, and I'll take out this transpose here. So we're doing part 1 for now. Okay, so what was my order for the selection matrix? So it's times and then plus. So now let's see. For each one of these, let's do, well, hang on. So let's do for each plus reduce. So this is all the numbers added together. And then we can also do the same thing for the times reduction. And we can put them together in a matrix by doing this laminate concatenate thing. And so for each one of our math problems, these are the results of multiplying them together and adding them together. And now it's as simple as just multiplying by our selection matrix. And you'll see that there's a bunch of zeros there, but that's okay because we are just going to ravel it and add the whole thing up anyway. And that gives us our part 1 answer, something, something, 978. Looks like the correct answer. And like I was saying, the only thing that we should have to do is for our input, if we transpose all the numbers in those math problems, we should get our part 2 answer. So 106 something something 949, which is our answer for part 2 as well. Okay, so now all that's left is kind of just cleaning this up a little bit. This, looking at it, can be a train with a couple modifications. So let's do like for each right tack, we need a jot here and a jot here, and we'll call that function f. Oh, you did not like that. Why is that? So no, that should. So right tack, this thing. Oh, I don't even need the right tack. That's why. Sometimes, you know, trains are fancy and all that, and they oftentimes can save you quite a few characters. But sometimes it's a pain, you know, counting up the arity of, you know, this is like the right function in the train, this is the middle function, this is the left parameter, but we have to like, you know, jot it together. You know, sometimes it can be fun. So then we do fm, we get our part 1 answer. We can get our part 2 answer like this. If we want to be ultra fancy, we can do them both at the same time by doing like im catenate over enclose. And if we look at the shape of this, this gives us 2 elements. And then for each one of these, we can do f. And this gives us our part 1 and part 2 answers in a single go. If you put all this together, not that one, it looks like this. So 4 lines. The first line, you know, it's a little bit long. You could do this matrix, like the character matrix calculation on a separate one. But sometimes I'll go for the long line if I can just like, if I can just keep rolling with it after the assignment. So, yeah, that's day 6, but let me give you a bonus implementation. So we have our character matrices, and what if, you know, we wanted to be a little bit more hacky and do some like string manipulation and try and do this with eval. So let's have a function on m, and we'll run this for each character matrix in there. We will pad the left side with spaces, and then we can ravel it into a vector, and then we can put the reduce primitive on the left. The only question is what operation to use, and so let's see. We can take the last column of p for each first. This is the same as we were doing previously. If we want to use this in eval, though, the problem is that APL has a special character for multiplication, so we'll have to replace, we can do like equals right tack like this, and we'll replace it with the APL multiplication character, like so. Um, this can just be a value that we are putting on the left side of this function. Now we can do alpha concatenate, yeah, and all it's left to do is just eval it. And if we add all this up, we should get our part 1 answer. This transposition for part 2 still applies. So if we clean this up a little bit, this would be, yeah, this will be a right tack here, I think. Yep, and then F. And now if we do same line that we did previously to do part 1 and part 2, we should get the same answers. So if you do it this way, it ends up looking like this, which I think is a little bit shorter overall, and you can get away with 3 lines. The downside being that your friends will laugh at you for doing string manipulation and using eval. But, you know, trade-offs. So yeah, if you're willing to be a little more hacky, you can do it this way as well. Yeah, well, that's day 6. So most of the challenge just comes from doing this parsing, being aware of the white space. And like with most AOC problems, and possibly most programming in general, once you just have things in the right data structure, it makes it a lot easier to compute what you want. So that is day 6. Thanks for tuning in.